Hi guys, how are you? Today in this video I am going to discuss the GATE 2016 solution of organic part. So first organic question was ring flipping of the compound in the following conformation leads to. So this was the compound. Here the Br and CH3 both are in axial position whereas the OH is in equatorial position. So after ring flipping, what will happen? The axial group will come into equatorial position and the equatorial group will come into axial position. So after ring flipping, here the Br which is here, so it will be in axial, and Br was in axial, so it will come into equatorial, and here the CH3 in axial, so CH3 will be in equatorial. So this will be the conformation of this compound after ring flipping. Next question, total number of lines expected due to spin-spin splitting of proton with fluorine and deuterium nuclei in the 1H NMR spectrum of the following compound. So how much line will observe for this proton after coupling with fluorine and deuterium? So fluorine has spin quantum number is equal to half, so it will split in 2s plus 1 way, so it will split one line into a doublet, whereas deuterium, which has spin quantum number equal to half plus half, that means equal to 1, so it will split 2s plus 1, that means 2 into 1 plus 1 equal to 3, so it will split one line into a triplet. So let's say this is the signal for this proton. So when it will coupled with fluorine nuclei, then it will be splitted into a doublet, and this is the value of JHF, whereas each signal will be splitted into a triplet by this deuterium, so it will be a triplet, and this is the value of JHD. This is also JHD, and this line will also be splitted into a triplet, and this is the value of JHD, whereas JHF is the coupling constant between hydrogen and fluorine, whereas JHD is the coupling constant between the hydrogen and deuterium. So it will be splitted into a doublet, and then it will be splitted into a triplet. So ultimately it was a triplet of doublet. So total number of line will be 6. The compound in R configuration is, so between these 4 compound, which one has R configuration? So as you can see here, in this compound a plane of symmetry will pass with this plane containing this CH3, H, this carbon and this carbon. So it will bisect this molecule into 2 equal halves. So this is optically inactive, and also for this compound, if we pass a plane containing this hydrogen, this CH3, this carbon, and also these 2 carbon and also this carbon, then the molecule will be divided into 2 equal halves. So this is also optically inactive. Now between these two, if we see this molecule in this direction, then if we project this molecule in Fischer projection, then we will get this ethyl and hydrogen, here will be the ethyl, here will be the hydrogen, and as we seeing in this direction, then hydrogen will be in left and CH3 will be in right. So now this is the front carbon, this is the front carbon as we are seeing in this direction, and this is the back carbon. So we have to give preference this front carbon, these two group in front carbon, that is the groups in front carbon precedes the groups in back carbon. So these two groups are in front carbon, so we have to number this as 1 and this is 2, and for the two group in back carbon this is 1, so we will have 1 2 3 and this is 4. Now we have to rotate our eye in this direction, and so this configuration will have R. Whereas if we also seeing the configuration of this compound, then we have to see in this direction. So these two will be in vertical position, so here hydrogen, here ethyl, and here hydrogen is in left, so here will be hydrogen, here CH3. Now these two group are in front carbon, so these two group will precedes these two group, and between these two this will be 1 and this is 2, and between these two it will have higher priority, so it will be 3, it will be 4. Now 1 2 3, this is the anti-clockwise direction, so this will have configuration S. Next question, the most suitable reagent for performing the following transformation. Here a alpha beta unsaturated ketone is there, an azide group which will be converted into NH2, and this part will remain intact. So what will be our answer? The options are lithium aluminum hydride, H2PDC, PPH3H2O, lithium liquid ammonia. So this is Bart's reduction condition, this is catalytic hydrogenation, this is lithium aluminum hydride, that is hydride transfer reagent, and it is PPH3H2O. Actually this reaction is an important name reaction called Staudinger reduction. Staudinger reduction. So what is Staudinger reduction? In Staudinger reaction, a group containing azide group, a molecule containing azide group which if treated with PPH3H2O, then the product is RNH2, and azide can be converted into amine. We'll discuss the mechanism shortly. This is the azide. PPH3 as a nucleophile will attack into this carbon, so it will be formed. Now this negative charge, here will be the positive charge. Now this nitrogen will attack into this phosphorus, and a 4-member ring will be formed. Now one nitrogen molecule will be eliminated, and after this, if it is hydrolyzed with H2O, then it will be converted to an amine plus POPH3, that is phosphine oxide. This is known as Staudinger reduction. Next question, the major product formed in the following reaction. If this is treated with CH3I and then sodium bicarbonate MeOH warming condition, what will be the product? Now as you can see here, the nitrogen is a good nucleophile, and CH3I, this is a good electrophilic center, so it will attack into here, and simple SN2 reaction will take place. So first the product will be, when it is treated with CH3I, it will be a quaternary ammonium salt. NC2H5O2 CH3 plus I minus. Now from this quaternary ammonium salt, if it is treated with a base, that is sodium bicarbonate MuH, it is a basic solution. If it is treated with a base, then what will happen? OH minus, it will take this acidic proton. Why it is acidic? Because one carbonyl group is there which has a strong electron withdrawing, which is a electron withdrawing group. So this OH minus will take this proton and the conjugate base will be formed. Now this is a stabilized anion, so it will undergo resonance with this carbonyl group. Here plus I minus N is 3 C2H5 whole 2 plus I minus. Now from this anion an elimination reaction will take place, so the product will be this mechanism is actually U1CV mechanism, that is elimination via conjugate base. Next question, the major product formed in the following reaction, that is a proper gel alcohol which is treated with 2 equivalent of lithium amide, that is LiNH2, and 2 equivalent in liquid ammonia. This is liquid ammonia, and then C2H5Br and then H3O plus. So here 2 equivalent lithium amide base is used. So 1 equivalent will be used to abstract this hydrogen. So first 1 equivalent, this will be used to abstract this proton. So it will be the corresponding anion will be formed. Then another equivalent, it will take this proton, because this proton is connected to sp hybridized carbon and it is quite acidic, so NH2 proton will abstract this proton and the corresponding anion will be formed, that is this anion will be formed, and between in this anion 2 nucleophilic center is there, one is oxygen and another is carbon. Now if it is treated with CH3 CH2 Br, this is the electrophilic center. Now between this is an ambidentate nucleophile, so it has 2 donor center which will use, in this case this is a strong nucleophile than this center, because carbon has lesser electronegativity than oxygen, so this negative charge will be is much more available than oxygen. So this will attack into this carbon, and here a SN2 reaction will take place. So the product will be CH3 CH2 C triple bond C CH2O minus. Now if it is treated with H3O plus, that is work up with acidic condition, then it will be converted to OH group. So our product will be this. Next question, the major product formed in the following reaction. So this is a furan and this is treated with acetic anhydride in BF3. So as you see the condition, BF3 is a Lewis acid, and in acetic anhydride in Lewis acid, this is a Friedel-Crafts acylation condition. So here acyl carbocation will be generated. Now this acyl group will attack by this furan. So acyl group will come in this position, that is position 2, or in this position we have to determine this, or in both these two position or both these three position. Now as furan is not that much active ring like pyrrole. In pyrrole, here nitrogen has lesser electronegativity than oxygen, so here the donating electron density in this ring is very much higher. So in this condition, more than one electrophile will come. So here generally electrophilic substitution occur in more than one position, but in case of furan only in one position electrophilic substitution will take place. So where it may be either 2 or 3. So what will be the product? Now we'll draw the sigma complex corresponding to 2 attack and 3 attack. If the electrophile will come at position 2, then the corresponding sigma complex will be this. Now this is the resonance stabilized carbocation. So the resonance structures are this. Resonance structures are this. It has three resonating structure. Whereas if attack occur at position 3, this is 2 in this position, then the corresponding sigma complex will be here EH and here with the positive charge. Now this can be resonance stabilized with this oxygen EH, here with a double bond, here is the positive charge. Now this cannot do not have another resonating structure, because here the oxygen has one lone pair and we cannot move this pi bond here, because then the oxygen will have 10 electron in its surrounding, but it is not possible as oxygen is in period 2 elements. So it is stabilized by 2 resonating structure, so the attack will preferentially occur in position 2. So the product will be this. If you have any doubt regarding this video, please let me know in comment box.